Hello, I'm David Patterson. I have a degree in applied mathematics, in engineering, and I have a PhD. I'm still talking to you about infinity. This is the third and last part of the introduction to ordinal infinity. The next part, part 4, will be about applications in quantum mechanics. Part 5 will be about applications in computer science and programming. Part 6 will be also applications, but I haven't yet decided whether that will be applications in terms of solving divergent series, evaluating divergent series, or applications in calculus. The infinity that you're taught in school is not particularly useful in applied mathematics. The infinity that I've introduced in parts 1 and 2 here is a lot more useful in applied mathematics. There are many different types of systems of infinite numbers that have been developed over the years, and when I get closer to the end of all these parts, I might go through and list and compare all the different types of infinite numbers that have been invented over the years. If you see something that you don't understand, just skip it. You'll find that the passage will make perfect sense without it. In particular for this talk, if you don't know what a complex number is, then you might want to skip the sections which deal with complex numbers. But most of what I'm introducing here doesn't require any more real knowledge than a knowledge of real numbers and limits. First, a review of parts 1 and 2 of this talk. Ordinal infinity is written using the lowercase Greek omega, which is the lower half of the normal infinity symbol. Parts 1 and 2, I gave 4 ways to generate the field of ordinal infinite numbers, all of which have been known for nearly 50 years. One is to say that if this fact is true for a sufficiently large real number, then it's true for infinity. A second is closure under the operations of plus, minus, times, divide, and all the rules that go with that. Commutative rules, associative rules. Third way is developed by the mathematician John Horton Conway, and they're called surreals, and they come from generate a number by bracketing it between two sets, a smaller set of numbers and a larger set of numbers, and the new number must lie between the two. This is called a Dedekind cut, after an earlier mathematician called Dedekind. And the fourth method that I introduced in parts 1 and 2 was Robinson's hyperreal numbers, which you get from adding sequences of ordered numbers together. But now for something new. What of cos of infinity? For large x, the value of cos x fluctuates between -1 and 1. Because cos of x fluctuates, it can't be fitted into the rigid ordering required for the number line of ordinal which contains ordinal infinity. Can't be fitted into the real number line, in other words, in this case. So whereas log of infinity, square root of infinity, infinity squared, and e to the power infinity are all valid ordinal infinite numbers, cos of infinity is not. Cos of infinity can be expressed as a series. Cos of x can be expressed as a series which is quite similar to the series of e to the power x. Every second term reversing in sign. And if you know complex numbers, you'll know that the relationship between e to the power x and cos of x is this. Now 1 plus omega squared on 2 plus omega to the 4th on 24 minus omega to the 6th on 720 is a perfectly valid ordinal infinite number. But cos of infinity, which is the same continued on to infinity, is not. Now what that means is that closure under operations of plus, minus, times and divide only works if there are a finite number of such operations. With only a finite number of such operations, you cannot get a fluctuation at infinity. Whereas with an infinite number of such operations, you can. There are several ways to define a fluctuation. Thinking of statistics here. We can define it by the range of fluctuation, the median value, the interquartile range, etc. Or we can define it by the mean, standard deviation, skewness, etc. Either way, let's define the average value at infinity to be the average value at sufficiently large x. Also, let's define a pure fluctuation as one with an average value of 0. So cos of infinity is 0 because its average value is at large x is 0. Sine of infinity is 0 because its average value at large x is 0. This is the simplest way to give a fluctuating function a unique value at infinity, which is the only way to fit the infinite limit into the number line containing ordinal infinity. So, given an arbitrary function, f of x, split it into the sum of a smooth component, the mean value of f of x, and a pure fluctuation, f dash x, and discard the pure fluctuation to get a unique value at infinity. So, f dash of infinity equals 0, and f of infinity equals the mean value of f at infinity. Limits. Standard analysis has two different and in fact incompatible types of limits. There is the shift-invariant limit at infinity, which assumes that infinity equals infinity plus 1, such as the limit of n tends to infinity of 1 on n equals 0. It's pretty standard mathematics. And also there's the non-shift-invariant limit at a finite number. So the limit as n tends to 1 of n minus 1 over n squared minus 1 comes from what's called L'Hopital's rule, and that evaluates to 1/2. This is not shift invariant because 1 is not equal to itself plus 1. So the limit as n tends to 2 is not equal to the limit as n tends to 1. In standard analysis, this incompatibility, this difference between the two limits, doesn't matter, because the shift-invariant limit only applies to infinite numbers and the non-shift-invariant limit only applies to finite numbers. The hyperreals, however, and ordinal infinity in general, has a non-shift-invariant infinity. Infinity is not equal to infinity plus 1. So we need to separate out the two types of limits. So putting the two previous slides together, we come up with this. The shift-invariant limit at infinity remains the same as in standard analysis. Using the Dedekind cut notation, A, B, from part 2 of this talk. Now, A is a set of numbers less than the number we're interested in. B is a set of numbers greater than the number we're interested in. And the A-B defines a number which is greater than the smaller numbers and less than the larger numbers. So limit, the standard limit, the shift-invariant limit, n tends to omega, or n tends to infinity, of 1 on n, is a number less than 1 on big N, 1 on all the natural numbers. And 0 is less than 1 on all the natural numbers. And this approaches 0, so 0 is a perfectly good thing to call the shift-invariant limit. But the non-shift-invariant limit at infinity is different. To distinguish between the two, I'm going to write a superscript star after the lim for the non-shift-invariant limit. So lim star n tends to infinity of 1 on n is the Dedekind cut, in this case between 0 and all inverse natural numbers. And that is the infinitesimal 1 on infinity, which is not equal to 0. Can't be equal to 0. It's greater than 0. And I'm going to set the limit of pure fluctuations to 0 in order to preserve the ordering of ordinal infinity. So the limit as x tends to lim star of x tends to infinity of f of x is the mean value at infinity plus lim star of the fluctuating part at infinity, and we reject the fluctuating part at infinity to say that the limits lim star is equal to the limit of the mean. This is a bit of a complicated slide, so if you don't understand anything on it, just skip it and the rest will make sense. 0 times infinity equals 0. I've said that before. In part 1, I showed that that statement is necessary to separate infinity from negative infinity. I can also show this with Robinson's hyperreals, which I discussed in part 2. For example, 0 times e to the power infinity is the sequence 0, 0, 0, 0, 0, 0 times the sequence e squared, e cubed, e to the fourth, etc. Multiplying out each term in order, you get 0, 0, 0, 0, 0, 0, etc., which is 0. In other words, 0 times an infinite number equals 0. All right. Also, lim star as x tends to infinity of e to the x squared, which is rather large when x tends to infinity, times e to the power ix, which is a complex number, is e to the power omega squared, it's large, times e to the I omega, which is pure fluctuation, so is reduced to 0, equals a large number times 0 equals 0. That is very, very useful. There is a difference between e to the power I omega and the absolute value of e to the I omega. In the complex plane, talking about complex numbers again, the absolute value of e to the ix equals 1 for all x. So the limit is absolute value of e to the I omega equals the sequence 1, 1, 1, 1, 1, 1, etc. equals 1 is not equal to the absolute value of 0, which is 0. Expressing the same thing a different way. Cos of infinity equals sine infinity equals 0 because they are pure oscillatory functions, pure fluctuations. But cos squared plus sine squared is the sequence 1, 1, 1, 1, 1 equals 1. Expressing the same thing in yet another way, cos squared of infinity is a half of 1 plus cos times 2 infinity. Cos of 2 infinity is a pure oscillatory function, reduces to 0 in the infinite limit. So cos squared of infinity is a half. Well, here are some useful, or perhaps not so useful integrals. For every function here, I give the integral from 0 to infinity. It doesn't matter here whether I use 0 or infinity because the results are finite. This particular infinite result here, I could probably refine it to say which infinity it is, but for practical purposes it doesn't really matter. The last line is integration by parts, and this helps to relate one to another. So for instance, x cos x is minus value of sine x. X cubed cos x, because it's a 3, is minus 3 times x squared sine x. X squared sine x, because the x squared is 2 times x cos x, and so on. X to the power 0.25 cos x relates to x to the power minus 0.75 sine x. Anyway, those are new integrals and their average values using the new limit. Take-home messages. The number line containing ordinal infinity, that's say, if you're talking about the axis of a graph, for instance, or the limits of an integral. This is strictly ordered, so cos of infinity can't be an infinite ordinal number, even though infinity squared is. A pure fluctuation has 0 average. Usually that would mean 0 mean. In the previous table, mean and median are the same, so it doesn't really matter. Standard analysis contains two different definitions of limit that become incompatible when one moves up to ordinal infinite numbers. One of them is shift-invariant and the other is not shift-invariant. For evaluating a function at infinity, split the function into a mean part plus a pure fluctuation and define the non-shift-invariant fluctuation removing limit as lim star as n tends to infinity of f of n is lim star of x tends to infinity f of x, so natural numbers, real numbers, is the mean value at infinity. This has practical applications such as in evaluating improper integrals, improper integral being one that can't be solved using standard analysis. Well, that completes this talk. The next one will be about applications in quantum mechanics. So I've completed the introduction to ordinal infinity, the introduction to limit, and moving straight on to applications in the next talk. Bye for now.